Hi, I'm Jeff Bryant. I'll be giving a talk with Jose Martin-Garcia about eclipses, and we're going to be giving a presentation concerning the microsite that we put together that highlights the 2017 total solar eclipse visible through most of North America.
So this summer we were very lucky to have a solar eclipse so close to home. So it was a major event here in the US. So here at Wolfram we decided to do something about it, and we called it the PrecisionEclipse project. And let me put this bigger. And it had many parts. So first of all, we started by improving our own astro functionality, also the date and time related functionality, because in order to do astronomical computations, you need precise timing and careful treatment of several types of type systems. We did a lot of research on the theory and history of solar eclipses, and in particular, Stephen got really interested in the history of solar eclipses and how humanity has been able to get more and more precise predictions of eclipses. Then we did an independent computation of contact times for the eclipse. This is a bit of what we will describe later. Stephen wrote a blog. Jeff also wrote 2 blogs. You have links there, and Jeff will talk about them later. We produced the PrecisionEclipse.com microsite, in which you were able to get all these times and maps and more interesting information. And we also, with all the information we had collected, we also had there a notebook with related information in the microsite. So many things. So the plan of the talk is that I'm going to talk about first the first part, and then Jeff is going to talk about the second part of my list of topics here. Okay, so if you want to make predictions about eclipses, what do you need? So you need basically 3 main ingredients. First, you need to have good data for the position of the sun, the earth, and the moon. You need ephemeris data, precise enough. Second, you need good orientation on the earth. And third, you need careful way of linking those 2 things with time information, taking into account things like finite speed of light. So fortunately, NASA provides very precise data for the positions of moons, planets, even spacecrafts. And these can all be collected in what they call kernels. And they also provide software to interface to those kernels, etc. There is a link here to go and get some of those. So what I've done here is, rather than interfacing with those kernels in real time, because they are huge, what I've done is just to extract some interpolation functions which contain the information that we will need. So these interpolating functions report the positions of the sun, the earth, and the moon in a 3-dimensional coordinate system, which is called the J2000 coordinate system, and the units are astronomical units. So this is quite precise. And then to do the computations, there are some other numbers we need, like the sun radius, the moon radius, the Earth semi-major axis, etc. Right? And it is all in astronomical units, or here astronomical units per second. Okay. Some basic facts is that, of course, the Earth is moving, and it's moving around the sun like 30 kilometers per second. The moon is moving around the Earth at a speed of about 1 kilometer per second. And for example, these numbers coincide with what we get from our function. So I'm asking here, what's the norm of the vector between the moon at second 20,000, 20,001? I forgot to say that I'm going to be measuring time from seconds in GMT time from 1200 to 2400. So there is an axis of 43,200 seconds, right? And the eclipse here happened around 20,000 seconds, right? So this is an axis of time in seconds from 12 hours GMT time that day. Something also interesting to know is that the rotations are all happening basically in the same direction. So the Earth is going around the sun in this direction. The Earth is also rotating around itself in the same direction. the moon is rotating around the Earth in the same direction and rotating around the same direction. So this is a manipulate that allows you to zoom and see the cones of shadows, etc. But I don't have time to do that, so I'll leave it here for you to play with it. As I said, something fundamental is the control on time. And there is a basic problem in all of this. The basic problem is that there are two systems of times which are important in this game. First, as in astronomy, you need a homogeneous axis of time that in which each second is the same one, it counts second, another second, another second. For Earth, the important thing, the civil time, is the rotation of the Earth. But unfortunately, the Earth is slowing down in its rotation. Actually, when it was created long ago, billions of years ago, a day was just a few hours, say 5, 6 hours. Since then, it's slowing down progressively, and the measurements currently say that it's losing like 2 milliseconds per century each day. So, so therefore, that's dt. So this is the number of days in a century. So each day is losing that amount. If we now count one of those amounts the first day of the century, two of those amounts the second day of the century, etc., each day we end up with this number. And if we replace the numbers, that means that each century is 31 seconds longer than the previous century. And this is something that accumulates. And so in order to have a synchronization between the astronomical time and the civil time, we need to add the so-called leap seconds. So in order to have these under control, a number of time systems have been introduced. There is the International Atomic Time, which is controlled by atomic clocks. There is the terrestrial time, which is the time used by astronomers, which is just this shift, constant shift with respect to the previous one. UT1, which is the time that is following the sun. And then UTC, I mean, the sun in the sense of the rotation of the Earth. So it's not homogeneous because it's slowing down with the Earth. And then UTC, which is a time that has been created to be always a number of seconds shifted from time, but that number of seconds changes with time. So these are the leap seconds. At the end, the whole thing comes out to this formula in which you have the relation between these two fundamental times, the time of astronomers, the times of the rotation of the Earth. The difference is delta t, and we have this difference plus this thing, which is measured every day. And there's a web page where you can get information about it. And they are actually do predictions, and they predicted that for that day of the eclipse, it would be that amount. So finally, we need this time. So this means that if we go to NASA's page, they will report things in TT time, but when we were looking at our watches, it was this time. So this is the correction that we had to measure. And this correction is included in all the formulas that I have here. So we don't have to worry about it, but if you don't worry about this, you would get all the times like 70 seconds wrong. Well, the eclipse has this area, so that's the sun, that's the moon. The Earth will be kind of here. And if the Earth happens to be in this smaller area here, we would have a total eclipse of the sun. Here, if you are looking from here, you have a partial eclipse of the sun. And if you are looking from somewhere here, you have an annular eclipse of the sun. Fortunately, we were very close to the apex of the cone, but we were on this side. And so we had a total eclipse of the sun. Now, these are polygons that you may have seen reported. So this was the partiality area. So if you were in one of these places, you would see a partial eclipse of the sun. If you were in this band here, you would see a total eclipse of the sun. So the first question is, why does it have this weird shape? Well, in an orthographic projection, it looks better. But still, why, for example, this part here, and why this is kind of waving, etc. So the way to understand this is, I think, is this one. So this is the Earth. It will be rotating. We are looking from the sun. So the Earth is rotating. The moon is passing in front of us. And now look how this central point here is the total area. The Umbra. So this is the point from which you would see a total eclipse of the sun. This is the penumbra cone. So this, from any of these other points, you would see a partial eclipse of the sun. And you see how this is always touching the lower line, and this point is following this line here. So this basically explains what that happened that day. Okay. Okay. Now, what about the orientation of the Earth? Again, we need something that tells us how the Earth is oriented with respect to the J2000 coordinate systems that is used in astronomy. So fortunately, again, there is an organism, the IERS, that worries about this and reports daily also the rotation metrics that you have to use to go from one coordinate system, the one of the Earth, our datum ITRF00 used in geography, to the J2000 coordinate systems of the astronomers. So we have those interpolating functions. This is the angle of rotation. This is the axis of rotation. So that's a matrix, which is the orientation. So using this, for example, this is a typical computation. So this is the angle between from our location. This is the angle between the sun and the moon. And you see, you have to use all four functions: the Earth position, the orientation of the Earth, the sun function, the sun position, and the moon position. Every computation related to eclipse needs the four of them. And so we can plot now that, and this is in our time axis from Champaign when it was the moment of maximum eclipse, when the sun and the moon were aligned. However, this angle is too large. Here we always saw a partial eclipse, not a total eclipse. Unfortunately, this computation is actually wrong because it's not taking into account the fact that the speed of light is finite. So we need a bit more of computation. So we need a fixed point computation that takes into account that there are large distances, that the speed of light is finite, and recomputes time again and again until it converges. And so, for example, to do a computation of where is the Umbra center, we have to do that. And so, for example, if I don't do that doing that iteration, I get a given geoposition for a given time, the time that was reported for Carbondale, maximum eclipse. However, if I do only one iteration, which means it doesn't do any iteration at all, the position reported is that other one, and I will be making an error of 22 miles. So it will be this. So this is the path of totality. That's Carbondale. This is the center that we get if we do the computation correctly. This is the center that we get if we do everything correctly, except for taking into account the speed of light, which is shifted. And we can do that for many, many centers, for many, many times during the eclipse, and we get there, with that simple function, we get, you see, where the center of the total part was every 5 minutes. Okay, so yeah. So now, so now this is Jeff's part. Is this correct? That is right. Okay. Thank you.
Okay, well, as you can tell, Jose did a lot of math work. My part's going to be a little bit more pretty to look at, maybe not quite so complicated. This was a very large team effort. It was not just me and Jose. Jose did a lot of the back-end math, but we actually had some members of our web team in-house that actually did a lot of the deployment. But we actually were able to deploy the PrecisionEclipse computation website, PrecisionEclipse.com, where you just go there, kind of like on Alpha, and you just get an input field. But the intent is you put your location in. You put an address, you could put a city. Most people probably just put in their city, but it would even work if you were on your mobile phone, and it would actually have a button that allows you to get your GPS location. And it would give you a personalized report for that particular location at the times of the eclipse. This is the front page. There we go.
And once you enter a location, so here, for example, this was the result for Champaign, you get a report. There's a number of panels here. The top left panel there shows you the location where you currently are, where you made the query from, and Champaign in this case. You can see the path of totality going down into the left, right there. And then more of a zoomed out view kind of showing you nationally where is that with relation to the whole path as it goes. Then over here it's basically just a text report kind of giving you precise times. Partial eclipse begins and how long it lasts. As Jose mentioned, here in Champaign we didn't get a total eclipse, so we can't really say much about how long did totality last. Best we can do is tell you how long partiality lasted. So, but then below that we get kind of a time sequence here showing how much of the sun is covered at what times. And you can see here, down here, just below the diagram, you can see we've got the actual time. So partial eclipse started here in Champaign at 11:53 a.m. We had our maximum eclipse, which was about 93%, I believe, and partial eclipse ended at 2:44. And then down below, a little bit, sorry, I'm not used to max here. There we go. We get a little bit more extended time sequence, kind of showing the progression of the eclipse as it should have appeared for the location you queried for. This was all made possible from Jose's math behind the scenes. Now, other locations, that's an example of partiality, you got a very similar report. So this is for Carbondale. Carbondale we keep mentioning because Carbondale, Illinois was the peak of the total solar eclipse. Anywhere in the nation, that was where you were going to get the absolute longest eclipse, anywhere. Not by huge amounts. I mean, anywhere along the path of totality, you would have seen something that was about 2.5 minutes long. But Carbondale was the kind of the technical computed maximum. Another point of interest is that in 7 years, there will be another total solar eclipse that will also go through Carbondale. So if you were in Carbondale, you're actually going to be at this prime location for 2 follow-up eclipses. But in Carbondale, you can see here the time of the eclipse. We have a little bit more detail here because totality, shown here, began at 1:20 and ended at 1:22, so or a little after. So about 2.5 minutes there, and you get the actual times for that. But other than that, it's basically the same kind of visual representation that we got for the partial eclipse, except that you can see the sun got totally blocked. So that's the general report that you would get from an eclipse query. Now, how did we assemble these things? Well, the maps panel is obviously done with geographics. So, once you've got a given geo position, here we've got Carbondale once again being used as an example. Very small amount of code is needed to actually construct that map. You can see that we've got a geomarker that shows you the user's location, and then we're using the function in Wolfram language solar eclipse to just give you the total phase polygon that we use as an overlay to geographics to show you the path. Now, that's just a basic interpretation. The exact implementation used a custom geomarker here that you can see. That's just a graphics primitive that was just drawn. You can use any custom geographics marker you want just by drawing a graphics primitive, and then you can hook it up. So if you're interested, that's in the talk. You can look at that closer. But then it's just a slight modification, though, of what we did up above, where you just put in your custom graphics code there for my pen and how to align it. And then the other map panel was just a zoomed-in version of that. So basically all we did was change the geo range to 50 miles so that you zoomed in on that location. So that covered the maps panel. Now, the biggest thing that you want to compute for an eclipse is the timings. That's the important part that we were going for here. Try to be as precise as possible. And so typically when people who deal in eclipses, they refer to the 4 contact points, and they call them usually C1, C2, C3, and C4. Here in Champaign, all we had was partiality. So you had the point where the moon first touched the sun, that's C1, and then it just kind of drifted just a little bit north. Here in Champaign, it drifted north of the south edge of the sun, and then it disappeared. So we had C1 and C4, just the point where the moon first touched and the point where the moon just barely left. Those are C1 and C4. But if you're in totality, you also get C2 and C3. And this is where, keep in mind, during a total eclipse, the moon is just slightly larger or exactly the same size as the sun. So typically there's a time frame where the moon is just on top of the sun, and it takes just a few minutes for it to move over, and then it's gone. So totality doesn't last anywhere near as long as partiality does. So, but if you've got a total solar eclipse, you can actually compute the contact points, the second and third contact points. And that's what we were going for And in visualizing this, we ran into an interesting thing that we hadn't anticipated. Basically, Jose did all the hard work of computing what times things should be, what's the position of the sun and the moon to very precise values. So we got the altitude and azimuth for a given location of the sun in the sky, and then we went to plot it. So here you can see we've done a calculation here where we've got the data object at a certain time, the time that we want to investigate. We've computed the moon's position and the sun's position at that time. We've got the sun's radius and the moon's radius. And then we basically plot these as disks with graphics. So as you can see here, there's just a graphics head, and then we've got two colored disks, essentially. But the time that we've chosen was actually supposed to have been after the moon had contacted. Yet when we plot it, they're not even touching each other. We thought we had a big problem. What's wrong with our code? Why is the moon not touching the sun? It turns out it all was a problem with projections. Graphics does not do any projections. It actually takes place on a flat plane. But the sky is more like a dome. If you don't take that into account, it actually throws things off. So we ended up switching, using the exact same disks, but we switched to geodisk and then geographics. And there you go. Using the exact same computed values, it's just dependent on how you plot it. You've got to take that projection into account or it'll be off. So that's actually, it was a very important part in getting that visualization to work. Geographics is your friend. Now, the white version here, this is just a subtlety here. We had two different versions of the visualization on the microsite. One had a white background where you don't see all the moon. You only see the part covering the sun. We're actually using a thick white circle right here to act like a mask that covers up the rest of the moon outside the sun. So that's how we got the white background there. For the black background, when we actually did want to see the moon. So there we just don't use we just dark background. And I don't know if you can actually see that with the contrast on the screen there, but the moon, the complete disk of the moon is visible there. It's just slightly darker than the background of the graphic. Okay. All right. So that's basically how we summarized it. We are planning, let's see, do we have a link to the, let's see. You want to talk about the Geek Notebook a little bit? Yeah. Okay. Okay. We actually also, something else we had on the microsite is we had this kind of an additional information notebook that was presented. So if you're interested in eclipses, you might be interested in these other things. And this is available if you go to the microsite, which is still live. You can still go there and use it even though the eclipse is past. And once you're done, you go to the bottom of the report and there's a thing about full details. And if you go to the full details, there's a whole bunch of additional calculations that we put in here that you might be interested in, how eclipses are carried out, how plots were done, things like that. I encourage you all to visit that. It's pretty detailed. There's some pretty complex calculations in here. So we've got various ways of plotting in geographics your location. We've got actually an API call to the microsite, so you can actually generate the grid of contact times yourself locally. How to generate eclipse maps for a particular state that are annotated with times. Plotting the light curve. This is essentially, I think this was obscuration. Was this obscuration, or do you remember which? Okay, so there's a subtle difference between obscuration and magnitude. Okay, so that was the obscuration. And we've also got get the distance to the location of, so how far are you from the distance of maximum duration? We've even got some Wolfram alpha calls here to generate star charts showing you what the sky should look like. Obviously, the moon and the sun are on top of each other, so you should get a solid red disk for time of totality. Even some slightly unrelated things. We've got data on what's the sunspot count. Where I was at observing the eclipse, we actually had people that were observing the sun well before the eclipse started, looking at sunspots and doing all kinds of stuff. And then we've got some really complicated stuff, explicitly solving the main lunar problem numerically. And I'm not going to go too much into detail here. I'll kind of leave this as homework for you guys. But this is something that Michael Trott and I know Jose were both heavily involved in that kind of goes into the details of how you actually solve using ND solve, things like the location of the moon, shape of the moon's orbit. Need to wrap up here. I think we're basically done. So very quickly, I'll leave this for most of you to go through as homework, but if you have any questions, me and Jose are both going to be around. There's lots of astronomy questions that I'm sure that could come out of this, so thank you.